Welcome back, AP Statistics. This is Chapter 3, Displaying and Summarizing Quantitative Data. All right, in the last section, we looked at categorical data displays, like this one over here, this bar chart. Now we're going to be looking at quantitative data displays. Again, a quantitative variable is a variable with numerical values that have meaningful units, like US dollar, for example. Histograms. This is the first type of graphic display that we're going to be looking at for the quantitative variables. When analyzing quantitative data, each data value may be placed into bins of a certain width called classes. So look at this frequency table right here. We have different classes, and data values can fall into any of those classes. Apparently, there are 3 values between 2 and 2.3 inclusive. All right, so moving on, we have 2.4 to 2.7. Apparently, we're rounding to the nearest tenth. And there are 2 values that fit into this class. There are 5 values that fit between these class limits, and so on and so forth. And so we make a bunch of bins here, and then we see how many data values fall into each of those bins, and that gives us a distribution of quantitative data. But we haven't made a graph yet. How do we get from here to here? Well, the frequency table to the right gives the distribution of GPAs for a sample of 20 high school seniors, and that's all fine and good, but if we were to display it graphically, we would allow the data to speak a little more. So let's do that. The distribution may be represented graphically using a histogram. That's this guy right here, where the classes are along the x-axis, and the frequency, or how many data values fall into each class, is on the y-axis. Now a note here, you'll see that these boundaries, the 2.4, 2.8, 3.2, so on and so forth, we need to understand how these boundaries should be read. This bar here contains all values between 2 and 2.3. Well, then what's the 2.4 doing? Well, that is the lower extremity of the second class, all right? 2.4 to 2.7. All right, so 2.8 is not included in this bar, just like 2.4 is not included in this bar, okay? So if we had a data value of 2.8, it would go in this bar. But if we had a data value of 3.2, it would go in this bar, all right? So each of these bars represents the value at the left end all the way up to, but not including, the value at the right end. That is common practice for histograms. You'll see histograms of all kinds in this book and on the AP test. You'll get used to how to read them. The bars of the histograms are, we would say, contiguous. There are no gaps except those that would indicate that no data values fit into a particular class. So for example, say there were no data values in this second class right here. Say we had a 0 instead of the 2 here. Well, then there would be no bar. Well, does that mean that we scrunch this side of the data right up next to our 2 to 2.3 class? No. We would want to leave it empty, all right? That's important in our data analysis. Let's look at some more detailed histograms. A relative frequency histogram, we've seen that term, relative frequency, before. It's just like a normal histogram. So we have a normal histogram here. We have possible values on the x-axis, frequency on the y, how often they occur in our data on the y-axis. Except the y-axis in a relative frequency histogram, like the one down here, shows the percentage of data values in each bin rather than the number of values, right? So let's look at this tallest bar right here, the bar that corresponds with a magnitude of 7 or 7.1. Each of these bars has a width of 0.2, all right? So we have 7 to 7.2, 7.4, 7.6, 7.8, and all the way up to 8. So this bar right here, the really tall one, corresponds to data values either 7 or 7.1, those magnitudes rounded to the nearest tenth. So looking down here, we can see this bar, this tall bar, corresponds to this tall bar right here, except instead of saying, oh, in our 1,318 earthquakes that caused tsunamis, about a little less than 200 of them were between a 7 and a 7.1. Down here we can see that about 16% of the total were between 7 and 7.1. Right? So that's how we would read a frequency histogram versus a relative frequency histogram. We're not looking at counts, we're looking at the proportion that each of these bars makes up of the total 100% of our data. Well, what's the difference between a bar chart and a histogram? Well, simply put, bar graphs are for categorical data, like languages, for example, whereas histograms are for quantitative data. So if you see a quantitative variable like magnitude of an earthquake that caused a tsunami on the x-axis, then you are dealing with a histogram. Now we're going to make a histogram on our calculators. This is a useful skill that you're going to need throughout the year. Below is a list of the number of bugs caught by 25 children at a summer camp. So here are the data, and we're going to make a histogram of this information on a graphing calculator. You can find instructions to do this on page 42, but I'm going to take my own digital calculator and show you how to do this. So here is a calculator, kind of like one that you're going to be using. So how would we make this histogram? Well, first we need to go into Stat. Seems appropriate for a class like this. We're going to hit Enter or the number 1 to go into option number 1, which is Edit. This is home base for statistics. This is where we begin most of the time. So we go to Edit, and I've already input this list. How do you input a list? Well, say I want to enter the value 22. It's the first value in our data set. I would hit 22, and then I would hit Enter, and that takes me to the second value. All right? So I've typed in all 25 of my values for each of my 25 campers. I did that already for convenience sake. Now I'm going to plot my histogram. There's stat plot right here. I can access that by hitting second and then stat plot. Now I have this first plot here and the plot is on. You very well may have all of your plots off. That is okay. Click that first plot. Make sure toggle between on and off and make sure the plot is on. Hit Enter. Then for type, go down to type, and if you go to the right, you will get many different kinds of plots. We'll be using most of them, not all of them this year. All right, some of them are not terribly useful. Some of them are extremely useful. And this is among the most useful. So we're going to go to what looks to be a bar chart, and we're going to make sure that we have list 1. If something other than list 1 is there, list 1 is right above 1. We would say second list 1. All right, and frequency, we'll cross that bridge when we get to it. Just leave it at 1. And here we go. We're going to, here's the graph button. We're going to graph our histogram, and we get nothing. Well, why is that? Well, this is in Zoom Standard. All of our data values are in the teens, at least. This X value is 10. That's not going to fly. Now, is there a convenient way for this calculator to graph our data as a histogram? And the answer is yes. I'm going to show you a trick. You're going to hit a button called Zoom, right dead center in the top row. You're going to go down a ways, click, 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 all the way to Zoom Stat, which is number 9. On this calculator, maybe a different number on another calculator, but scroll down to Zoom Fit. Here's number 9. I can either click 9 or I can hit Enter. And your calculator, through programming that I do not entirely understand, will make a beautiful histogram, and that is a good graphic representation of your quantitative data. We can tell that the most popular class is this one right here. And then we have some people who are underachieving in their bug collection, some people who are overachieving, but most folks are in the middle right here. Okay, very good. Okay, we're going to talk about stem and leaf plots now. Consider the following data set on the pulse rate for a sample of patients. All right, and there's my sample, and there's my pulse rate. By the way, fun fact, you'll learn a lot of fun facts in AP Stat. You'll notice that each of these values here are multiples of 4. Well, why is that? Well, a common way to conveniently calculate your beats per minute of your heart is to count the beats over a course of 15 seconds and then multiply by 4, all right? Well, that makes sense. 15 seconds is a quarter of a minute, so you multiply by 4 and you get your beats per minute. What that means, though, is that your beats per minute, if you're using that technique, are in they're multiples of 4. All right, so there's a little tidbit there on how this process is often done. So you have the quantitative variable pulse rate in meaningful units, beats per minute, and we have a frequency here, okay? But this is obviously a histogram. This is not a stem and leaf plot. This is a stem and leaf plot, right? How do we read this? Well, let's look at the bottom. 5, 6. This corresponds with 56. The tens place is on the left, the ones place is on the right. Let's look at this row. This is a little more confusing, but you'll get it really quick, I promise. 6 is the tens place. Our next data value in the list is 60. And the value after that is 64, and there are 3 of them. So we have 60, and then 64, and then another 64, and then another 64. And then we move on to our next one. Oh, wait, the tens place is still a 6. What gives? Well, we're following the pattern laid out in our histogram right here, okay? So any value between 65 and 69 would go into this bar right here. There are 4 68s in our data, and so they would stack up nicely right here. And then we have 70 to 74, and then 75 to 79, 80 to 84, and then 85 to 89. All right? There's a little key at the bottom of a lot of these stem and leaf plots. 8 bar 8 means 88 beats per minute, right? There you go. There's your stem and leaf plot. Cool thing about a stem and leaf plot, if you're going from lowest on the bottom to highest up top, if you turn your head to the right, there you go. I see you're turning your head to the right. The stem and leaf plot resembles a histogram in reverse, right? So look at this histogram. Look at this guy right here. You'll notice that it's in reverse. That does mean that maybe a more convenient way to give a stem and leaf plot is to start with the lowest number at the top and the highest number at the bottom, but that's usually not how it's conventionally done. Whatever. All right, let's look at this stem and leaf plot. Now, this one is okay, but you'll notice that each row has only one value in the tens place, as opposed to this one that we just looked at, which had 2 rows for the tens place 6, 2 rows for the tens place 7, and 2 rows for the tens place 8. I mean, this is fine, but it is, shall we say, crowded. It would be nice if we were to spread things out a little bit. That allows the data to speak more, all right? What we're dealing with is a situation where we don't have enough bins to allow the data to speak maximally. This representation says more about the actual distribution of the data. We have a sufficient number of bins. Here we only have 4 bins, one for each of the tens places. Things are just a little crowded. The data don't really speak well in this representation. For this set of data, it's better to have the ones place be split into two rows, one for 0 to 4 and another from 5 to 9. All right. Then we have this, which is a better representation. You can see a little comparison right there. Sorry for that motorcycle that went by if you just heard that. There you go. Stem and leaf plots. For large numbers, that you won't see this terribly often, but in case you do, for large numbers, we can feel free to truncate, all right? And to truncate, we're literally getting rid of a place value, all right? That's what truncating means. It's not rounding, and we'll talk about that in just a moment, okay? Truncating is literally getting rid of a place value, okay? So here's a data set, small data set, but it's in the hundreds. 432. To the left of the bar is the hundreds, 30, but where's the 2? It doesn't matter. These numbers are so big that a data value of 432 versus a data value of 430 is probably not a huge difference. So we can just truncate the ones place, and this would be interpreted as 430, 400s and 310s. Again, 540 and 571, you got 540 and 570, well, there should be a 1. No, we've truncated the 1. 638, we truncate the 8. Not a huge difference when the numbers are this big, all right? So we truncated the ones place, and we note that truncating is different than rounding. Rounding, we would move up to a nearest place, but for the 638, we just leave 6 and 3. It doesn't turn into a 4. It's not like, oh, 8's above 4, 5 and above, give it a shove. No, truncate, we don't care. So there you go. So here's an example for you. Make a stem and leaf plot for the data values, those. And just as a heads up, this ones place of 5, we're going to use a 0 for the tens place for 5. All right, so 5 just has a ones place, unlike 12 and 14 and all the other data values that have a tens and a ones place explicit. We're just going to use 0 for the tens place for 5, right? So give this one a go, pause the video, try it, and unpause the video when you want to see the answer. Okay, let's look at the answer. Boom. We have 0 for the tens place, 5 for the ones place. For 1 for the tens place, we have 2, 4, and 9 corresponding to 12, 14, and 19, and so on and so forth. Dot plots. This will be the last plot that we're talking about in this section. So like a stem and leaf plot, a dot plot is useful for a visual display of a small, that is fewer than 100, data values, data set that is. Each data value represents a dot in the dot plot. So this is a dot plot here depicting the number of seconds it took the winning horse to complete the Kentucky Derby. All right, I imagine there was some kind of a rule change from here as opposed to here, or something is different. And we're actually going to explore these data by color coding each one of these data points, and each one of the colors represents the conditions of the track on the day. So you'll understand why these data land over here as opposed to these data landing over here. I imagine there was some kind of rule change nonetheless, but there's a little bit of explaining power. Sometimes the track is in good condition, sometimes the track is in not so good condition, and that will change the time it takes to win the Kentucky Derby, right? So we'll be coming back to this, but first, you try to create a dot plot for the data below. Look at the example over here, pause the video, give it a go, check your answer against mine when you're done. All right, let's continue. So there's an example of a dot plot. I've included all the values in between and listed by ones. Probably the best course of action here. We don't need to work over wide intervals like here. 74 to 95 with a little bit of grit and determination. You can put the dots in this dot plot right here. All right, we're going to talk about the quantitative data condition. You'll remember the categorical data condition, that the data are counts or percentages of individuals in non-overlapping categories. We saw this condition had to be met in order to use a pie chart, okay? So these data right here constitute non-overlapping categories. You have percentages that add up to 100%. Those are non-overlapping categories. We could put that in a pie chart, and it would actually be rather useful to do so. These categories we found in the last section were overlapping because it is certainly possible for someone to have a smartphone and a computer, or a computer and a tablet at the same time, all right? And these data add up to, or these counts, these percentages, add up to way more than 100%, all right? So these are overlapping categories, and we would not be able to use a pie chart. That would be silly to do. The quantitative data condition says that the data values are of a quantitative variable whose units are known. All right. This condition must be met to make a histogram, stem and leaf plot, or dot plot. All right. So all the plots that we've talked about so far, we need to have data values are of a quantitative variable whose units are known. All right. We don't just need to know that we have a quantitative variable. We need to have known units, and the units have to be meaningful. All right, it's not just some random index. It has to be like miles per hour or US dollar, like we saw earlier in this lesson. This is why categorical data can't be made into any of the graphs. The data has to be quantitative. All right, so in order to make a histogram, a dot plot, stem and leaf plot, you need quantitative data. And this sounds like an absolute no-brainer. But I can almost guarantee you that the AP test, and I know for certain that your textbook is going to try to get you on this one. They're going to try to get you to think that a quantitative sort of graph can be used for categorical data, all right? Look out for that. They're going to try to get you on that. Sometimes they're pretty sneaky. Make sure the variable you're considering has units that are known and units that are meaningful,